I'm coming here to do the introduction.
Yeah.
Okay. Now, need to turn off the echo.
We can't turn it off.
We can't turn it off. Okay. Well, no, you can.
But we can only,
You can temporarily mute here.
yeah, it's not coming from here, it's coming from there. We need to do a lot of running to turn it off. It's not practical.
Okay. So okay.
I turn
so,
off this
sorry.
microphone when we stop talking.
It's like a Duran Duran video.
Okay.
Introduction there.
Maybe I'll go down there. We're delighted to have Andre Bernabik here today. He couldn't jump across from San Sebastian because he tested positive for COVID, but we really appreciate that he's still coming to the meeting and giving us 2 lectures. So for his first lecture today, he's going to tell us about flat bands, projected and unprojected Hamiltonians, and mapping to topological heavy fermions. Hello, Andre. We normally have about an hour for the talk and 20 minutes for questions, roughly the breakdown.
Thank you so
Thank
much.
you for being here. Yeah.
Thank you so much. And I feel really terrible that I didn't make it there. I made it 80% of the way, but I managed not to get COVID in the US. The moment I landed, I got COVID here from an American collaborator of mine. So American based. So, such is life. But hopefully I can entertain you for 2 hours today and tomorrow. So the first part of the talk is going to be about flat bands and projected Hamiltonians. And then tomorrow, I'm going to tell you how to improve on this and make everything way more explicit and much more clear and much more easy to compute by doing unprojected Hamiltonians and a mapping that basically reveals the important degrees of freedom and their role in the problem. So this work has been done in collaboration with a lot of it with Jida Song, who's now a professor at Peking University, and with Jonah, Dimitru, Aaron, and more recently Jabin. Of course, we've benefited a lot by collaboration with more senior people, including Ali Yazdani and Dimitri Efremov on the experimental side. So I wanted to take sort of the first 10 minutes to make an advertisement first for a database of flat band materials. And with that, introduce some of the properties of the flat band materials that we're going to use. And then go to the twisted bilayer graphene case, which will serve as an example for flat band materials. It's a special kind of a flat band in the sense that it's got some extra particle hole symmetry, which lattice problems don't have, stoichiometric materials don't have. But other than that, a lot of the formalism that we'll use before can be applied there, and then we'll go from there. The thing that I want to get to today is to understand the many-body correlated state at integer fitting in twisted bilayer, or at least the ones where there's no strain in the sample, through the physics of projected Coulomb Hamiltonians to the flat bands. And I'll show them results that other flat bands have similar physics, and sort of stress the importance of the non-trivial topology, or even if the topology is trivial, non-trivial quantum metric, non-trivial quantum geometry of the wave functions on these Hamiltonians. So why are flat bands interesting? This is sort of an old topic. One of the first remarks on flat bands is by Volovic, and on superconductivity in flat bands. It basically remarked that superconductivity in flat bands is transition temperature would be proportional to the interaction rather than to the exponential, usual BCS exponential form of the Fermi surface. But of course, there's prior work than that, dating back to Haber ferromagnetism papers by Mielke, and then Wigner crystallization, super solid formation. More recently, and this was spearheaded by the Finnish group of Päivi Torma et al. They basically showed that non-trivial topology even if the band is flat, can lead to interesting things, such as a bound, for example, for the superfluid weight, even if the kinetic energy is zero. So this relates to the question that I had for your last talk. It would be interesting to kind of have a topological SYK Yukawa type of Hamiltonian, where basically you wouldn't have to introduce kinetic energy. The superfluid weight would come out, even though the kinetic term is zero, would come out from the non-trivial quantum wave functions of the problem. And the existing flat band techniques, at least in that exist today, are kind of restrictive, but I'll show that a generalization of basically Lieb's 1989 method can kind of exhaustively take care of all the flat bands in stoichiometric materials. Twisted bilayer is a kind of a different example, as it is not a stoichiometric material, and we'll get to that later. Now, the type of flat bands we're looking at are a bit different than the flat bands, or not a bit, but rather very different than the flat bands that come from atomic insulators or atomic limits. So what we're really not interested in is the atomic flat band, where I can construct a Vanya center of the electron that sits exactly where the atom sits, okay, and that is exponentially localized with, you know, a very tight localization around the atom. So that will give a flat band, just because there's no hopping between between different atoms. But we're not interested in that. What we're interested in is flat bands that come sort of from interference, from having non-zero hoppings everywhere, for example, but or not everywhere, but nearest neighbor, next nearest neighbor. You can make a generalization of however long you need to get the hopping in real space, but where the flat band comes from interference of the wave functions. So we could be interested, for example, in flat atomic bands, but that are obstructed. So these are atomic bands where the Vanya center of the electron sits in between the atoms. So this would be kind of a covalent bonding chemistry picture, which really you can now put on strong quantum mechanical footing based on things like topology and real space indicators, which indicate you whether a bond is covalent or not, just by knowing the bands in a DFT calculation. So these will be interested in, because even though they're atomic, so they're exponentially localized, they do have some spread. They cannot be formed because the electron initially, the degrees of freedom sit on the atom. They have to be formed by atoms in different unit cells, really, and and they will have some overlap. So this will have some quantum geometry, and they will give non-trivial properties. And of course, we're interested in flat topological bands. And these flat topological bands, for example, one example of them is that of the Kagome lattice. Even though it's a flat band that's degenerate at one point with a quadratic band, if I break the degeneracy slightly, the only phase I can get into is a topological state, a quantum spin Hall state, if I have spin, for example. That degeneracy can be broken with spin orbit coupling, but I'll immediately go into a quantum spin Hall state. There's no other state I can go into. So we'll be interested in flat topological bands. And not, can you hear me? Okay, so thank you. Okay, and a general construction of these exact flat bands on a lattice, of just exact, so I don't mean even exponential bandwidth, exact not zero mode, but any energy, really, exact flat bands on a lattice, was actually initially given by Lieb in 1989. So Lieb said the following: if you take a sublattice L, a lattice made of two sublattices, L and L tilde, and there's only hopping between the L and L tilde sublattices. And this hopping can be anything, here we denoted it by S of k, any matrix, any sum of harmonics, however, whatever order you want to get to. If the lattice L is larger than the lattice L tilde, so for example, the unit cell of the sublattice L has more atoms than the unit cell of sublattice L tilde, then you will have NL minus NL tilde zero modes in this band structure. And this is clear because there's a chiral symmetry in this model, and the chiral symmetry forces you to have this matrix be rank deficient, basically, if NL is different. Well, S of k is rank deficient if NL is different than NL tilde, and you will get to a situation where you have exact zero modes. Turns out that the chiral symmetry is actually not necessary. The full generalization of this, of Lieb, and we can still call them generalized Lieb, there's really bipartite lattices, but really you can have hopping between the L tilde and L tilde lattice, any type of hopping. B of k is another, any type of harmonic. And as long as the function A of k, harmonic between the L and L sublattice, satisfies the following properties, it has a flat eigenvalue with degeneracy larger than NL tilde, you'll still have flat bands in this model. So these spectra will no longer be chiral, which is good because a lot of real materials don't have chiral symmetric spectra, most of them. Even even graphene doesn't really have a chiral symmetric spectrum if you look at it, even though around for low energies it does. This type of Lieb construction, generalized, still works and creates exact flat bands. Now, the good thing about this construction, and the thing that, of course, came out with the advent of topology, is that just by knowing the orbitals on the L tilde lattice, you can immediately get the character, the eigenvalue character, and by knowing the eigenvalue character, and furthermore, more than eigenvalues, real space indicators, other topological things that aren't based just on eigenvalues of the bands at high symmetry points in the Brillouin zone. Just by knowing the orbital content on the N and L tilde sublattice, you can immediately obtain the orbital, the eigenvalues of the flat band. So how does this work? Well, you're able to prove a theorem. All the bands in the model have to have the eigenvalues of the atomic limits coming from the N and L tilde orbitals, so orbitals into sublattices. Those are all the orbitals in the system. I have some localized states on them because I built my tight-binding model. They represent all the bands in the system, and we know that there's a map between the localized orbitals in real space and the momentum eigenvalues in the Brillouin zone. So, given the orbitals on the L plus L tilde lattice, I know all these eigenvalues. I don't know their order, so I don't know that this is gamma 1 and this is gamma 5, but I know that at the gamma point, I should have gamma 1 plus gamma 5 plus gamma 1 plus. This is for the Lieb lattice, for example. Okay. But then you also know, you can prove that the upper band here, this band, for example, has to have exactly the same eigenvalues as this lower band, and you can see that they're the same. K1 here is the same as this one, and moreover, they represent the eigenvalues of that a band would have if it was induced from the localized orbital of the L tilde sublattice. So again, based on this construction is based on the past decade of work where we can take orbitals localized on lattice and find their band structure, their eigenvalues of in momentum space. So we know that this is eigenvalues of the orbitals on L tilde and L tilde, and all this, so the two blue bands plus the red band, this for the Lieb lattice, have to have the same eigenvalues as L plus L tilde. So now you have this axiomatic equality that the eigenvalues of the orbitals on L plus L tilde lattice, so or the orbitals on all of your unit cell, is equal to twice the eigenvalue of the bands induced by the orbitals only on the L tilde lattice plus the flat band eigenvalues. So that means that the eigenvalues of the flat band are a difference of the eigenvalues of the localized orbital on the L lattice. You can see, so it's L plus L tilde minus 2L tilde. So it's L minus L tilde. So this band representation just is, this B means a band representation, and is just the eigenvalues induced by orbitals localized on a sublattice. So this is, so the eigenvalues of the flat band are the eigenvalues of the orbitals, of the bands of the orbit induced by the orbitals on the L lattice minus, and this is important, minus the eigenvalues of the bands of the orbitals induced on the L tilde sublattice. And this immediately gives you the following point, that this flat band is expressible, its eigenvalues are expressible as a difference of eigenvalues of two bands induced by atomic orbitals. So these L are localized orbitals, L tilde are localized orbitals. I induce the bands, they have BRL eigenvalues, BRL tilde, but there's this minus sign. So this doesn't guarantee, and in fact it's natural, that the flat band cannot be expressed usually, not in all cases. If the L orbitals can be deformed to the L tilde sublattice while respecting the symmetries, then you can subtract the L tilde sublattice from the L. But if you cannot, then it means that you cannot express the flat band eigenvalues in terms of eigenvalues of sums of localized orbitals. And that means that the flat band is topological. So in fact, this type of construction, lead construction, is a very natural way of getting topological flat bands. You don't get them always, just because sometimes the L lattice contains the L tilde sublattice through adiabatic processes in the lattice, where I can take the orbitals on the L and move them to L tilde adiabatically. But a lot of times you cannot. If you just have one orbital per site, you cannot, for example, because you cannot move it anywhere else if you're at the maximal Wyckoff position site, maximum high symmetry site. So in a lot of cases, you can only write the eigenvalues of the flat band as a negative, as a difference. And then you're stuck with having a topological band. And this is actually why, if you look at a lot of these line graph lattices, bipartite lattices, and actually compute the eigenvalues of the flat bands, turns out the flat bands are topological. And they're topological of a special type of fragile topology, but we're not going to get into that right now. So this technique of building flat bands, which I claim is kind of exhaustive for stoichiometric systems. And it's exhaustive because there's nothing else that can keep a flat band at every K except the rank deficiency in a rank deficient matrix that comes from, you know, some sort of bipartite structure with one side being larger than the other. It's the only thing that can give you degeneracy at every K if you don't have particle hole symmetry. And that brings us to the graphing case in a little bit. But if you don't have particle hole symmetry, which you don't have usually in stoichiometric materials, I claim this is sort of an exhaustive. I cannot prove it, but I claim it's exhaustive. And it allows you to immediately understand the eigenvalues of the flat bands from the eigenvalues of the L and L tilde lattice. Moreover, it also allows you to understand degeneracy points, for example, between flat bands and other flat bands. And I can explain how that goes. It's also axiomatic. If you cannot do this subtraction of the band representation at one point, then you're going to have a degeneracy point because there's nothing as a negative of a representation at that point. So this is a very simple way of getting the axiomatic bands topology of the flat bands, just by knowing the orbital characters on the N on the two sublattices. So this geometric way of doing things also can be actually implemented for a high throughput search of this database that we have, which is the topological quantum chemistry database, which basically doesn't have only topological materials, there's all materials in stoichiometric materials in the ICSD database in Karlsruhe. And once, since you have the bands of all these, you know where the atoms sit, and you can find out which geometric bands have this type of lattices that we've expressed before. And then you can then you look up their band structure, which has already been computed, and see how close the flat band sits to the Fermi level. It turns out out of about 100 materials, there's about 300 curated, really good flat band materials with a flat band around the Fermi level. So sort of 100,000 to about 300. And these are some of them, for example. And you can see how the flat band is very close to the Fermi level. And and of course, how their lattices are actually bipartite and have the same structure that we said before. Now, let's get to, now that I've done this introduction into flat bands, I want to get to the actual subject of the talk. It turns out that you can build a model of twisted bilayer graphene in exactly this way, actually. And this is the 10-band model. They didn't express it in this way, but it was later realized that it can be expressed in this way. The 10-band model of Poe et al. In 2019 actually expressed the twisted bilayer lattice as a bipartite lattice. It's a 10-band model, and they obtained the flat bands, even their shape, to be very close to that of TBG, and their eigenvalues to be very close to that of those of TBG. And they're topological, and I'll explain this in a little bit. They have to be topological in TBG. So there's these attempts to express twisted bilayer bands as Lieb-like lattices, basically. But as I'll show, all these attempts are actually flawed in the end because of a symmetry that makes TBG unlike these stoichiometric models, and in fact makes TBG anomalous at any bandwidth. And this symmetry is particle Hall, and it basically makes twisted bilayer graphene not being able to be written as any local orbitals at any bandwidth. So no matter how many bands I take, if I think of the Bister-Macdonald Hamiltonian, which is to start to describe TBG, which I'll introduce in a little bit, I won't be able to write any number of bands, no matter how many. Even if I go to infinity cutoff, as in terms of local orbitals. So the model is very anomalous. It's similar to the surface of a topological insulator, which at any bandwidth, if I neglect the bulk gap, obviously, and this corresponds to neglecting the graphene lattice bandwidth, for example, taking that to infinity, similar to a topological insulator, this is anomalous. But there's no, the surface of a topological insulator is anomalous, but here there's no surface in twisted bilayer graphene. The bulk is completely anomalous. And this is a unique feature of the continuum model in twisted bilayer. So with that, I want to go to twisted bilayer systems, but I want to basically point out that if I take out the extra symmetry that I'll be talking about, a lot of the conclusions, especially the interacting ones, as I'll show for the projected models, apply to other flat bands, not only the ones in twisted bilayer. So twisted bilayer, a crack introduction is the following. It's one layer twisted by a small angle from another. This small angle twist here is exacerbated. The crucial point is that you have a Dirac fermion from the upper layer, a Dirac fermion from the lower layer, and then at K point, and the K prime point, the same thing. So you basically have per spin 4 Dirac fermions per spin. Now, there's a new Brion zone that sets in, and this Brion zone is basically given by the distance between the Dirac nodes, K of the lower layer and K of the upper layer, which is just the K of the Dirac fermion times theta. When theta is small, this is the small distance and forms this first Moiré Brion zone. And then in order, sorry, I said something wrong. This is the K prime here. Okay, so this is the K prime, not, excuse me, not these ones. These are the same as these, obviously. Okay, but there's still 4 electrons per spin, 4 Dirac nodes per spin. Okay, so there's a new Briand zone. There's a new Moiré-Briand zone defined basically here. Okay, and if this angle is small, you can ask, how can I couple the valley K to K prime? The two Dirac nodes around the valley K form their own Briand zone. The two Dirac nodes around the valley K prime form they're also their own Briand zone. I can couple them, but this coupling is the perpendicular T of twisted bilayer graphene, the hopping between the layers over the in-plane T, to the power, in perturbation theory, the tiling of this Briand zone from, from here to here. And this tiling is KD, because this is the difference in the momentum over the Moiré-Briand zone momentum, KD times theta. So this tiling is 1 over theta. And hence, since T perpendicular is smaller than T, basically the coupling between this valley and this valley becomes 0. So there's an emergent symmetry, which is the valley symmetry in twisted bilayer. And then we are going to have a model of 2 Dirac fermions, okay, per valley, per spin. So we're going to talk 2 valleys and 2 spins, but per valley per spin is 2 Dirac fermions, and these are at single particle level good quantum numbers. Given that I just mentioned that we're going to have 2 Dirac fermions, two Dirac fermions per valley per spin, per valley, so at valley K, this is the Dirac fermion of the lower layer, this is the Dirac fermion of the upper layer, and then twisted bilayer, the Bicester-McDonald Hamiltonian, is basically putting a periodic potential at the Moiré length scale in between these 2 layers. And this periodic potential is actually given by I lost my, I lost. Right, okay, sorry. And this periodic potential is given by 2 coefficients, W0 and W1. And these coefficients are of order, this is 1 over roughly square root of 3 VF V Dirac K Dirac times theta in these units, K Dirac times theta, and W0 in the realistic sample is of order 0.8 W1. Okay, and they really represent the AA. You can see that this couples the A with the A and the B to the B, and so this is the AA coupling of the graphene of the Moiré lattice, and this is the AB coupling basically. So the moral of the story is that the Moiré lattice, as it forms, is large, is going to have some regions where it's going to look like bilayer graphene AA, and some regions is going to look like bilayer graphene untwisted AB, and this is going to alternate at the Moiré wavelength between those. And in those regions, in those 2 regions, we have 2 different hoppings because of basically reconstruction effects. And these 2 hoppings are almost, one of them, this one is 0.8 W1, and this is of the order at the magic angle, at which I'll define very soon, 1 over square root of 3 this, but normally it's the order, some rational number of order 1 times V Dirac K Dirac times theta. If there's any questions, please let me know. Okay, let me just try to kill the annotation. Okay, so I want to make a point that the symmetries of the twisted bilayer problem are very important, and this has only become kind of appreciated recently, although it was to be expected that this is the case. And the symmetries are the following: because in single layer graphene, the point K, the Dirac point, is not invariant under time reversal, which sends us to K prime, and not invariant under C2Z, which also sends us to K prime. It is, however, invariant time reversal times C2Z. So it's invariant under C2 times time reversal, which is this guy. And this is the symmetry of graphene of twisted bilayer. And you can see that this is a magnetic symmetry because it's not time reversal. It's time reversal with a point group rotation, and that's a magnetic symmetry. And that's fundamental to the understanding of the one valley problem, because the entire model is, of course, time reversal symmetric, but time reversal maps one valley into the other valley. And because it maps one valley into the other valley, the two valleys being decoupled, it doesn't matter. So they're block diagonal. So within one block, you only have C2 times time reversal. And of course, you have C3, C and C2X. But the other thing that you do have is an emergent particle hole symmetry. And this particle hole symmetry really is the emergent, is coming from the fact that the original graphene Hamiltonian, which is just K dot sigma, has the following particle hole at low energies. We're only interested in very low energies. These are energy scales of order up to 60, 70 electron volts, so very low energies. So the graphene Hamiltonian, just K dot sigma, has the following particle hole symmetry. And this particle hole symmetry propagates, it's a trivial symmetry, it propagates to the twisted bilayer. But in the case of the twisted bilayer, it has a little bit of a twist. It's well, the fact that it's unitary is not a twist. It's unitary also in the original graphene lattice. It squares to -1 in this case, and it anti-commutes with the C2X symmetry, which is still maintained by the single valley twisted bilayer system. So C2X symmetry is maintained, and particle hole anti-commutes with it. And you can generate this easily by looking at the values at the model of twisted bilayer. Now we can ask, initially particle hole was kind of dismissed. Now it's become kind of crucial. So we can ask, how good is it? Well, it turns out that it's as good as, sorry, go ahead. There's a question.
Yeah. Can I ask a question?
Yes.
Are these features also seen in the 10-band model that you mentioned earlier?
Particle hole is broken in that model.
In that model?
Yes,
Okay.
that's how they get around. That's a very good question. That's how they get around. So if they would implement particle hole, they wouldn't be able to write an orbital model. So the way they get around it is they break one of the symmetries. And every model that's written as in terms of a localized orbitals, with no matter how many bands you take, has to break either a spatial symmetry or particle hole. Thank you.
Thank you.
Thank you. So particle hole is extremely good, at least in the Bistrom-McDonald model. Now there's new suggestions that you should include some non-local terms that will break particle hole symmetry, but some of them will break particle hole symmetry at the energy level, but not at the eigenfunction level, which is what we're actually concerned about. And in fact, if you break particle hole symmetry, even at the wave function level, a lot of the formalism that I'm going to tell you about starting from now will still remain. It's just that some other states from a manifold of large symmetry might be picked based on how large the particle hole symmetry breaking is. But the particle hole symmetry allows you to fundamentally understand, and the other symmetries allow you to fundamentally understand the problem at a much deeper level than if you didn't have it. So the particle hole symmetry is extremely good. This is the error if you neglect particle hole symmetry, and you can see the error around 0.8 here is, less than 1% in the experimental case. Here the error goes large to 3%. This is W0 over W1, this AA coupling over AB coupling. Here the error goes to 0.3% because there's some gap closing, etc. So you have some, you have some fluctuations in the projector. It's not really real. So I would say it's less than 1% certainly, and is actually as good as neglecting spin orbit coupling is in graphene. And I want you to basically obviously compare that with the error obtained by imposing chiral symmetry on the model. which is this chiral limit that you can get. So the chiral limit is the W0 over W1 equals to 0. That's a limit of the model in which you can make some Landau level like construction of the flat bands. In this limit, the chiral symmetry gives you zero error because the model is chiral symmetric. But if you go to the normal, to the actual values, you get 90% error in chiral symmetry. So there's no chiral symmetry in this model in the realistic values. And this particle Hall symmetry actually has been essential to defining the large symmetry groups in this problem, such as U4 spin, which we'll get to later. Okay, now, why did I keep banging about this particle Hall symmetry? Well, well, if you have particle Hall symmetry, the eigenvalues of the flat bands are fixed. In other words, there's no other way to choose the eigenvalues. And you can see in this, these are the eigenvalues of the group described by C2T, C3Z, C2X. And now particle Hall, because I told you particle Hall anti-commute to C2X, fixes the representation. So if I had two bands around the Fermi level, okay, if I start with graphene, I know that I should have a double representation here because I have particle Hall, I cannot move it up and down. So this, I'll have the Dirac node here. But then particle Hall makes sure that these representations at the gamma and M point are exactly opposite in eigenvalues of C2X. Okay, and I don't know which one is above which. That's dependent on, you know, the parameters. But I know that if I have two bands, this is the set of their eigenvalues because, you know, whatever I have here, I have to have the opposite here and vice versa. And this is related by particle Hall, and it fixes the symmetries. And this basically tells you that the bands in twisted bilayer graphene at small angle are always topological if they're gapped. Why? Well, I told you that particle Hall fixes the symmetries. These are the symmetries. But I've also mentioned before that we actually have tabulated all the bands that can be induced by localized orbitals from any Wick opposition. We only need to tabulate the ones from maximal Wick oppositions, and then everything else is a sum linear combination of these. And these ones are tabulated here. And you can see that there is no way you can write down these bands as a sum of localized orbitals. So whatever, you know, these are some crystallographic numbers, but you don't need to know what they actually are. You can just see that there's no way to write these bands as a sum of any of these representations. For example, I could try to write numbers this plus this, okay, as these two. They would match at gamma and M, but they wouldn't match at K. And you go through this and you find out that you cannot write them down. Hence, they have to be topological. They cannot be written down in terms of localized orbitals. That's a definition basically of topology. And indeed, if you go and take the twisted bilayer graphene flat bands at different angles, as long as they're two per valley per spin. So you take the ones per valley from Bissell-McDonald model and you compute their Wilson loop or their Berry phase in one direction, which basically gives you the Vanier center in one direction as a function of momentum in the other direction. Then what you see is that it has a trajectory similar to that of a topological insulator. So for example, if the Wilson loop or Vanier center in one direction, in the Y Vanier center, as I move the momentum X in the Brillouin zone, winds between one part of the unit cell to the other part of the unit cell, then I have a Chern insulator. If there's two Vanier centers, because there's two bands here, and one winds in one direction, the other one winds in the other direction, and these crossings are protected by time reversal symmetry, that's a quantum spin Hall, etc. And you find that twisted bilayer graphene has exactly this type of, the shape does change a little bit as you change the angle. These are different angles, okay? But it does have the same winding as a quantum spin Hall state. However, it doesn't have spinful time reversal. This is per spin. So it kind of has the wrong symmetries for it, but this is actually protected by C2T symmetry. And you can think of these bands as two flavor electrons, one in up magnetic field and one in down magnetic field, or one band with Chern number 1, another one with Chern number -1. Okay, and we will use this label of twisted bilayer graphene of the bands, which is called the Chern basis. You can think of them as one band with Chern number 1, one band with Chern number -1 that kind of don't scatter into each other. Turns out that the single particle Hamiltonian is off diagonal in these bands. It's a sigma X in these bands, but it doesn't matter. You can always choose this gauge, which is called the Chern gauge. And this is how we're going to talk about these bands. Okay, so now we said that these bands are topological. And this is kind of a review of the previous slides. And the fact that these bands are topological prevents the obstruction of two-band symmetric and local lattice models. But initially it was thought that these bands are fragile topological, which means that you can add orbitals to these bands and build a vanirization or build a local orbital system. So by themselves, they're not. But if you add orbitals, they are. And this is the very fact that they did in the 10-band model. They added more orbitals and they were able to build a vanirization of the system. However, it turns out that in doing that, they broke particle hole symmetry. And particle hole symmetry is something that makes this model anomalous at any bandwidth. So this particle hole symmetry, which in experiments is actually seen as charge conjugation, so physics at plus filling is equal to physics at minus filling, is basically, I cannot go through the math, but what you have to trust me is that it proves that if you have 4n plus 2 Dirac points, okay, within a manifold which respects particle symmetry of any number of bands, then you have stable topology. And any number of bands cannot be written down as a localized orbital. For example, here I took 10 bands. We took 10 bands and did the Berry phase for 10 bands. And you see there's winding and all these crossings are actually protected. In fact, in this picture, we actually didn't even require full particle hole symmetry. We left it a bit broken as the Bisto-McDonald model, but you cannot see it because it's so weakly broken, less than about 0.5%. So the topology of the system is the same thing as the fact that within any number of bands from -E to E, you will have 4n plus 2 Dirac points and not 4n plus 4. You can never have 4n plus 3. Well, you can, but we'll get to that later. But you'll never have 4n plus 4. And these two Dirac points are, of course, the Dirac points of the flat bands situated here at K and K prime, K more A and K more A prime. And this is the same thing as the symmetry anomaly on the surface of a topological insulator, for example. It tells you that you can never have a single, you always have, with time process, if you have 2n plus 1 Dirac nodes, it will always be topological. But this is not on the surface of anything, it's in the bulk. So it tells you that the topology is equivalent to the existence of these two Dirac points, really. These 4n, neglect them, they can be anywhere. They can be here, they can be here, okay? They can be anywhere, they come in pairs because of particle hole. And this will become important in the next talk tomorrow. Now, the experimental facts of this system are the following. Now that we know that there's no local description, and we know this with its topology, you can see that there's flat bands at some magic angle in the system, and these are very flat. Look at the energy scales, and this can go from -4 to 4. So there's two flat bands per valley per spin. They can accommodate 8 electrons. We're going to count them from -4 to 4. If you're in the single particle model, everything should be a metal from here to here. Here you can see the AA stacking. These are the regions in the A stacking. These are the regions in the AB stacking of twisted bilayer, etc. So as you tune the gate voltage between here, anything but a metal shows up. Okay, so at every integer filling, or almost every integer filling, insulators show up. And then in between the insulators, you have superconductors. And then here you have strange metals, etc., linear resistivity, all kinds of things. Could you tell me how much more time I have today? Sorry.
You have about half an hour, including discussion.
Okay, thanks. Yeah, so please ask questions at any time. So it's clear that the single particle description cannot explain these insulating states, let alone the superconductors. We'll get to the quantum dot behavior tomorrow. So let's go to the interacting description. And today I want to show you an interacting description that's not particularly intuitive. But it doesn't.
Andre, before we go on, the experiments aren't particle hole symmetric. So what's going on?
Yeah, it's very good. So that's a big that's a big observation. So basically, in a lot of samples, the experiments aren't particle hole symmetric. I mean, the large features are. There's insulators both on both sides. There's superconductors both on both sides. But then you go in, and some insulator at mu equals to 2 has 10 times the resistivity of the mu equals -2, etc. So there's a huge amount of strain in these samples, and like C3 breaking, etc. So that some of those can break particle hole symmetry, because all you need to break particle hole symmetry actually is a for example a sigma z component here. Particle hole symmetry basically comes because this guy doesn't have a sigma z component, etc. So you can break particle hole symmetry and other things by strain. So I think that's what's going on. So this is the physics that would happen in a pristine pristine sample. So
Thank you.
thanks. Yeah. Very good. So all these insulators have to be described by the correlated insulators at filling not -4 and 4, not in the single particle gap. Okay, have to be described by interactions. And one way of doing interactions that's actually kind of nice is the strong coupling projection. It's not particularly justified because this gap here is not smaller than the Coulomb interaction that was measured in experiment. And we'll come back to that in the heavy fermion picture. But for now, let's just take it that we just take the Coulomb energy and project into these bands. And I'm going to go very fast through what happens. And the physics that happens is basically ferromagnets plus. So you take the Coulomb interaction, okay, you project into these flat bands, and you get this, the second term here. This is some plane wave. This is the Q in the Moiré-Briand zone. And these operators are the density operators, but projected into the flat bands. So they pick up these form factors. They pick up these overlap form factors. These overlap form factors are actually just overlap of the single particle states of these bands at momentum k. They're just UK plus Q, okay, plus Q plus the plane wave plus G. Have the M and nth band. Okay, so now two things come about. First of all, this Hamiltonian is semi-positive definite, and this is the fundamental thing that in the bilayer graphene was observed by Kang and Wafek, but in the it was also observed previously in superfluid problems by Hubert and by Torma and others. Now, if these wave functions were trivial, okay, if these wave functions were not momentum dependent, okay, were just trivial identity, right? Like a trivial insulator, for example, like a trivial band. If this function was trivial, this would be a classical Hamiltonian, like the Hubbard model with no kinetic term. And it would be immediately solvable because all these operators at different Qs if this is true, OQ1, OQ2 would commute. Okay. All of them at any Q. So, but that's not true. You have topology, and topology means that, excuse me, means that these form factors, i.e. the overlap, are K and Q dependent, which leads to non-commutative OQ, these are OQ1, OQ2, which leads to an unsolvable spectrum. In fact, it can be non-integrable. It usually is. Still, even in this case, some ground states and excitations are solvable. And this is a generic statement for projecting models, doesn't have anything to do with graphing. I'll show you some other projecting models of other Lieb lattices, for example, etc. And in some cases, depending on these form factors, if you make these form factors nice enough, but still not K and Q independent, integrable models can appear. And I'll show you some examples. But for now, we stick to these being those of twisted bilayer, the form factors, and they have this Hamiltonian is positive semi-definite. Because it's positive semi-definite, you can prove then that some states are ground states, and these are the states that are basically annihilated by this OG operator, depending on fitting up to some constants, and that you can get around. But if I have a state that's annihilated by this operator OG, then I'll have a ground state. So for example, under the term basis that I mentioned before, where bands are given by plus and minus eigenvalue in some limit, my O operator looks like this. Okay, where these are the operators in the new basis of the spin S, valley eta, and Chern band plus or minus 1. And you see that in this limit, which actually this is the chiral limit, this is diagonal in all these indices, then it's clear that I can form Slater determinant ferromagnetic states. And these are the Slater determinant ferromagnetic states at integer fitting. You just take one of the states, this is at fitting 1, you fill it up, and that will be an eigenstate of OG, and then will be eigenstate of this Hamiltonian. So this is, the quantum Hall ferromagnetism would show up like this also, etc. So all these Hamiltonians, you can get exact states in some limits, is basically at the fillings at which this form factor is diagonal in the structure of the density, okay, of the density operator. And then at filling 2, I can either bring this down. Of course, there's a large symmetry in this model, but I don't want to get to it right now because I want to get to it tomorrow in a more intuitive and much more intuitive and, from what I think, much nicer picture. Okay, so you can get the ground states. They're just ferromagnets. Sometimes they carry Chern number, and that was shown in some experiments, although the experiments that see correlated Chern insulators at exactly 0 magnetic field are just 2 of them. Most of them you have to apply a small magnetic field to get a quantized Hall conductance, still much smaller than from lambda quantization. What I want to go now to is, however, the fact that remarkably, or maybe not that remarkably, once you know that the ground states at these integer fittings are Slater determinants, but remarkably when we found it, is that you can get the excitation spectrum of these exactly. And the excitation spectrum is actually just a diagonalization of applying a flat band operator on this Slater determinant. You apply a flat band operator on the Slater determinant, and then you get, because I have 2 bands, 2 by 2, a 2 by 2 diagonalization gets me at every K, gets me the excitation on top of the correlated ferromagnets. And the excitation matrix, this RMG, has the following form. It's a convolution between the Coulomb potential and the form factors, 2 form factors. And there's a fundamental thing that comes here in that the dispersion of the one charge plus minus 1 excitations are basically related to the Frobenius-2D metric. This is kind of a generalization of the Frobenius-2D metric of these states, and hence they are intimately related to the topology or to quantum geometry of the wave function. If you had a Hubbard model normal Haber model with no kinetic energy, these will all be flat, right? Because I have a Haber model, I fill and I do one excitation, I get energy U. I do another one, I get energy U. So they would not be dispersed if I don't have a kinetic term, like I don't have here because it's projected. All the dispersion comes from the quantum geometry of the states. And you can ask, what's the dispersion like? It's huge. Dispersion is of order U. So look at the dispersion of the charge one excitation at filling 0. Charge one excitation is filling 0. And you see some interesting facts which you cannot explain yet. You see there's this at filling 0, particle and hole have the same dispersion. At filling -1, the electron excitation, so -1 plus epsilon, is very flat. The whole excitation is very dispersive, etc. But you can see that the dispersion is huge. It's of order U, and leads to new Landau quantization, new masses, new degeneracies that are completely different from the flat bands, from the bare flat bands. And this interaction, it also leads to the minimum of the interaction being at gamma, not at K, for example. So these are the results that you obtain from the strong coupling approach, which we cannot actually understand analytically. We can obtain it because they're very easy, but for example, this gap cannot be understood analytically, but I'll get to that later.
Andre, can you say a few words about what you mean by quantum geometry?
Right. So, so basically, so by quantum geometry, I just mean take the eigenstate at Q at K plus dk, and you subtract from it the eigenstate at K, and then you take its absolute value, and this is going to be some Gij of K, dki dkj, and dki dkj, and this Gij dkj is called the geometric tensor, or the metric, basically geometric metric tensor. Okay. And this cannot be flat. Okay, cannot be 0. So normally for a trivial insulator, where this, like for a one-band model, this would be 0, right? Because the eigenstate would not move. So the more this is varying from 0, and we can define some of its properties later, the more dispersion you'll have. If this is 0, you wouldn't have any dispersion. Now, for example, in a Chern problem, if I have Chern bands, this is bounded from below. There's no way this can go to 0. It has some bound from below. In this problem, which has two Chern numbers, plus and minus, the bands have you can actually still find a bound, and it's bounded by the Euler characteristic of the bands, which is another topological invariant of these bands, or the winding of the Wilson loop of these two bands. So whenever the band is topological, this has a bound on it. If the band is not topological, you can still have it non-zero. You just need not to have a trivial insulator. Have I answered your question?
I think so. So just to double check, we can use all the standard ideas of Riemann curvature tensor for the GIJs here.
Exactly. So yeah, so it's basically like doing GR on this large manifold of bands.
Mm-hmm. Thank you.
Thank you. Yeah, very good. Yes, exactly. It's very important. So you don't need topology to have non-zero GR, but you do need non-trivial bands in the sense of not having just localized. If I just have localized Wannier orbitals, extremely localized, this Gij geometric tensor will be 0 because the eigenstate won't move. So you need delocalized, some amount of delocalization. So the next thing that I wanted to show you is that I can actually solve through the neutral excitations, and in this problem too. And this all becomes because the ground state is a Slater determinant, because of the positive semi-definiteness of this many-body Hamiltonians. The ground state is a Slater determinant. It doesn't matter how many particles it has in it. Actually, solving for the excitation problem, for the neutral excitation problem, turns out to be a one-body problem, etc. So you can find the Goldstones, and you can see that these are ferromagnets, and you can find the Goldstone, you can find the dispersion, you can find the stiffness, analytically. Okay? But what's most important that I wanted to get to is the impossibility of Cooper pairing in these Hamiltonians. So you can do the same with a charge to excitation on top of the insulating ferromagnet states. You solve the excitation spectrum, and then what you see in the excitation spectrum for a charge 2 is no bound states. So when we looked at this first, you can see anti-bound states here, but no bound states below. And the lack of these bound states in the projected problem really kind of bothered us, but it turns out there's a simple explanation for them. The scattering matrix for the 2 particle is the 1 particle energy plus the other particle energy plus the scattering matrix pure between 2 particles. You can prove that this is positive semi-definite. Hence, there is thinking about the Richardson criterion for superconductivity, okay, where you need to get the charge 2 excitation having a bound state below the particle continuum of the charge 1 excitations. There cannot be a bound state in this because the scattering is positive semi-definite. Hence, there is no Cooper pairing from Coulomb project interactions in flat bands on top of integer filled ferromagnets. There's no Luttinger-Kohn effect without a kinetic term. These are projected states. And this is a theorem that you can that one can prove. Now, before I almost end, I wanted to basically show you that this is not something that you can do only in graphing. For example, we're doing this on negative Hubbard-U projected model. You can have Cooper pair excitations with negative Hubbard-U. Again, if I didn't have any quantum geometry, so if I just have a negative U Hubbard model, I'll just form pairs. They would just sit there, no superfluid stiffness as we heard in the last talk. But if I have topology and I go to a negative Hubbard-U model that's projected into some flat band, what you see is kind of a remarkable spectrum where the particle in some models that become integrable, where the particle continuum has just collapsed to basically one flat band. There's a huge amount of levels here, and the only thing you get is the collective modes. And this is the basically Cooperon, right? This is the bound state. This is the superconducting bound state, and the mass of the Cooper pair is given by the Fubini-Study metric. Actually, it's exactly given by the Fubini-Study metric here. So you can basically see that you can have with zero kinetic energy, because these are projected models, negative U Hubbard model. This is not on TBG; it's on some other flat band model. You can have superfluid stiffness, i.e., Cooper pair non-zero mass, with if I have non-trivial geometric bands. Okay, so with this, I want to end with this slide and go to tomorrow. And I want to point out that this projection, even though it answers the question of what's the nature of the states in the completely unstrained homogeneous sample, actually, in a way, leaves more questions than answers. For example, we know superconductivity appears in 2BG, but we know that the projected Hamiltonian cannot have superconductivity. So kinetic energy must be added to the Hamiltonian, otherwise there's no superconductivity. Locally, the nature of ground states is unclear. I'm just going to go one more slide to show you what I mean. Locally, the nature of the ground states it's unclear, and it's unclear what's responsible for the large Hubbard-U interaction and what's responsible for the itineracy in this picture. Now, the physical picture of how ground states are formed is also missing, although you do have this ferromagnetism momentum space basically, but it's missing, and there's actually too many degenerate states in some limits. If you solve this, Hamiltonian actually has a larger degeneracy given by more than just the symmetry group. So there's some extra degeneracies that you cannot really explain that shouldn't really be there. And there's also a quantitative question, since the projection removes these extra bands in the twisted bilayer graphene that are actually within the Coulomb energy scale. Moreover, none of the spectras, besides the fact that you cannot have Cooper pairing, None of the and the fact that you have gallstones, which we can understand very easily and prove. None of the other features can be understood easily in this problem. So, for example, I showed you that there's at fitting that the charge 1 excitation have a large dispersion. Okay, so what determines the gap? Why is the gap at gamma not at K? Okay, why is the largest gap? Why is the smallest gap at gamma not at K? Why are these bands here? They seem to be very flat. The band at the larger bandwidth of the excitation, they seem very, very flat. This is mu equals 0. Okay, why? This is generic. This appears in twisted bilayer at strong coupling projection generically. Why is this flat? Why is the bandwidth? Why is the band gap smallest at gamma? And for example, in mu equals to 1 here or -1, you can see that one of the electron has become very, very light. Okay, but the hole has become heavy everywhere. Why is that happening? Why, as I move between insulators at charge 0, at fitting 0, 1, 2, 3, these dispersions change and their flatness changes, etc. Moreover, look at the charge 2 dispersion. Okay, the charge 2 dispersion, we know there's no, for example, this is I think at fitting 1, the charge 2 dispersion, some fitting. We know that there's no Cooper pair state. We understand that, but there's anti-bound states, and these anti-bound states are actually very flat. Why are they very flat? Why are they there? Actually, this turns out this will be just a charging of a quantum dot of 2 heavy fermions that will come to in the next section. But why is this very flat? This projection cannot answer this. In the Goldstone spectrum, we also see, besides the actual Goldstone, we also see a flat band of Goldstone states. None of these questions can be answered by the projection. And with this slide, I close. But the biggest unanswered question by the projection comes from the experiments. And in the experiments, there's actually a juxtaposition between experiments which see or suggest the existence of local moments. And this, the clearest of these come from STM, where you can just visualize that the charge sits at the AA site much, much more, 90-something% more than at the AB sites. There's almost no charge at the AB sites. They're very, kind of like goes a little bit, right? And then you can see basically quantum Coulomb blockade behavior, quantum dot behavior, with a Hubbard U that's larger than the, certainly larger than the bandwidth of the flat bands and larger than the band gap between the flat bands and the next band. And then there's, of course, experiments which suggest delocalized electronic states. And these are all the superconductivity, etc. So in actually, like Pablo Herrero basically pointed me to one of his abstracts where he actually says that the correlated state features an unusual combination of seemingly contradictory properties, some associated with itinerary electrons and others associated with localized moments. And this cannot be answered in the projected, or at least is hidden in the projected methods of doing twisted bilayer graphing. But this will be answered by the heavy fermion interacting, well, single particle interacting mapping that we'll go through tomorrow. So thank you very much.
Okay, we're open for questions, although I don't know how we're going to do it with this dreadful echo. We're just going to try and fix it.
Okay.
Testing. Better. Okay.
Works.
A lot of material there. Questions? I can ask questions. So let me ask a sociological question to start with. How is the field that's worked on all of these beautiful lattice models responding to the notion that there's not just fragility, but real, I guess, stable topology in these systems? What has been the response of the community?
Well, the experimentalists, I think, I mean, the experimentalists, right, don't like to be associated with any theory, I guess. So they're you know, they're some of them are not mentioning it, but it's inescapable the fact that there's churn insulators in these correlated churn insulators in these problems. So you can see this guy, for example. So you can, you know, it shows up in very small magnetic field below Landau quantization. So what's happening here is that these theories do predict that there's a many body correlated churn insulator with churn state with churn number 4 that sits very close to the actual ground state. It's not the actual ground state at zero field, but it sits very close and gets stabilized by magnetic field. And similar things happen at larger. This is early data, but now Efetov has, for example, data that goes all the way to, I guess, 100 millitesla, I think, this churn insulators appear. So only a little bit of field, and you get the system in the right in the right churn insulator state. So these many body churn insulators could not appear if the wave functions didn't have topology. So I think it's inescapable that they have topology. I don't see so sooner or later I think it'll be adopted by all the experimentalists. I think the theorists clearly believe that, right, as we all do, but the experimentalists, a lot of them do believe it also. So I think the topology is the real, the kind of, you know, the distinctions between which topology is stable or fragile, those are, you know, they require one to work in the field to actually like pay attention to them, I think, right? So only few people pay attention to them, I think. So does that sort of answer the question?
Okay. Other questions? Gunnar's going to ask a question. Hang on a second.
Yes, just a question about the churn basis. So you said that the Hamiltonian is off diagonal, but you didn't say much about the actual eigenstates. So what are those integer churn insulators or integer quantum Hall ferromagnets that we actually see, and what is their eigenbasis?
Right. So the eigenbasis is so the eigenbasis, the Bister-McDonald model band basis is say 1 and 2, say 1 and 2, and the churn basis.
We're not hearing you, Andre.
Oh, it's
Hang on
very
a second.
flat. Citation is very dispersive, etc. But you can see that this. Can you hear me? Can you hear me?
Yeah, we can hear you again.
Okay, good. Right. So the churn basis is basically a linear superposition of the Bister-McDonald basis. So the basis in which the Hamiltonian, which is, you know, 2 Dirac nodes plus interlayer tunneling, is written. that's the eigenstates of that are 1 and 2, and the churn basis is just well, it's just 1 plus I times 2. That's the plus, sorry, C I this is right, C times I. This is the basis. Does that answer the question? And these are Slater determinants in the many body states are Slater determinants in this basis. So this is at every K. At every K, I fill up all those states.
Were there 1 and 2 the two valleys? What was 1 and 2?
The 1 and 2 are the so I have the Bister-McDonald Hamiltonian has 2 bands. right? And these are the eigenstates of the two bands. So this is, so these are, they have orbital, etc. content, but these are just these are 1 and 2. They're just the two bands. So I solved the Bicester-McDonald Hamiltonian, HB, let's just HB. UM is equal to EUM. And M is 1 and 2 for these bands. Right. Just, of course, these U's have structure on the A and B, as you said. They have structure on the A and B sublattice. They have structure on the plane wave basis. They have their each U1 and U2. So by 1 and 2, I just label the eigenstates of these two at every K. This is UK. And then the Chern basis is Chern basis is 1 plus C times I times 2.
Okay, thank you.
Plus my, okay. So yeah, thanks. 1 plus. And then at every K, so this is right, this is U1, sorry, U1 plus U2. At every K, and that's what you do. That's how you fill the Slater determinant. Does that answer your question, Gunnar?
Yeah, it does. Thank you.
Thank you.
What about the Coulomb interactions? You didn't really touch on whether those preserve the particle hole symmetry or not.
They do. They preserve all. They do. So okay. So basically, at a given filling, so there's, yeah, that's a very good point. So let me be more precise about this, actually. Sorry. So the particle hole changes the tells you that the Hamiltonian at filling mu, the many-body Hamiltonian filling mu, can be mapped into many-body Hamiltonian filling minus mu. Right now, so this is what, right? So this is what it tells you. There's two things that the particle hole induces. So first of all, the particle hole is a charge conjugation, tells you this is true, and this Hamiltonian has that property. Now there's another thing that this particle hole induces, which is the following. This Hamiltonian has clearly a U2, which is the spin and charge in one valley. Spin charge in one valley, in valley eta equals to 1. And it has another U2 symmetry, which is spin and charge in valley eta equals to 2. But because it has the particle hole, the unitary particle hole symmetry, if you combine it with, so particle hole symmetry, remember, change the Hamiltonian from K, the single particle Hamiltonian from K to minus K. But C2Z, change it back to K. So P times C2Z is an operator which is local, changes K to K.
Mm-hmm.
This is a local operator, and actually C2Z changes values. So it changes eta from 1 to 2. Okay.
Mm-hmm.
And it actually provides the extra Pauli matrix to raise this group to fully U4. And this is the flat U4 that you know about.
Mm-hmm.
It has to get U4, you need this particle hole symmetry times C2Z operator. So it's P times C2Z creates a local operator which changes K to K but flips the values. So it allows you need only one more matrix to flip the two U2s into the other, and by commutation you can get the whole U4 group. And hence the particle hole gives you also a U4 symmetry at a given filling. So those are the two effects of the particle hole.
Very good. Well, I think what we will do is let you rest, and we're also going to go for lunch, and we'll look forward to your talk tomorrow morning.
Thank you so much.
Okay, thanks so much.
Thanks.